In this video, we're going to consider motion in one dimension. In some sense, this is reverting back to freshman physics, where we only considered motion in one dimension. But there are certain things that are clearer if you restrict yourself to just one dimension. And we will take things a little bit further than we did in 2305. Plus, there is actual cases in real life, of course, of one-dimensional motion. You can just think of a train, perhaps, or a ski lift as examples of one-dimensional motion that are quite practical. So if we are moving in just one dimension, then we know, of course, that the potential energy is just given by a line, by a regular single integral from some starting point to some ending point of fx of x dx. So we will move on the x-axis, and here is xa, and there's xb. We also know that this is equivalent to saying that, again, don't forget the minus sign. This is equivalent to say that the force in the x direction is equal to minus du dx. Okay, so that's what the formalism looks like. Now, if we're working in just one dimension, we can easily plot what the potential looks like. The potential might have this form if we're dealing with a conservative force, and as we've shown earlier, the only requirement for a conservative force in one dimension is that it depends only on position. That's all we need to know. So this is automatically conservative. So if we have a conservative force, we have a potential like this. And with this definition, we can see that there are forces that point in the opposite direction of the slope of the potential, right? So here we have a positive slope. That means that the potential, or that the force, is pointing towards smaller x in the negative direction. And here the slope is negative, so the force is pointing in the positive direction. Like that. Now, if we're looking at these points here, I'm going to call those A, B, and C. There, the force is 0. So at those points, we have no force, and if a particle, or a train, or a ski lift finds itself at this particular point, it will not move forward and it will not move backward, well, provided that it also has no velocity. Right? And these points are known as equilibrium points. Now, there are two kinds of equilibrium points. We can see that if we were to place a particle here, then even the slightest motion away from the equilibrium point, there would be a force that pulls on it and accelerates it away from that equilibrium point. So that's why this is known as an unstable equilibrium. Stable equilibrium. And there's one here too. We'll call that point D. On the other hand, if your particle is here at point A or at point C, and it moves slightly away from the equilibrium point, then there's a restoring force that will move it back towards the equilibrium. So these 2 points, they are stable equilibria. Now, just looking at this plot, it's pretty easy to see what is a stable equilibrium and what is an unstable equilibrium. But it would be nice to have a mathematical expression for it as well. And that's readily available. We know that the curvature here depends on the second derivative. So to restate this then mathematically, if the second derivative of u, d to u, the x squared, if that is greater than 0, that means that u is in a minimum. So that means that we have a stable equilibrium. On the other hand, if d2u dx squared is less than 0, well, then u is maximum. Or we are at an unstable equilibrium. All right. Of course, you can also have d2u dx squared be exactly equal to 0. In that case, you don't know what you have. It might be a minimum, it might be a maximum, it might be what's known as a saddle point, in which case it's not an equilibrium at all, really. But for the cases we're going to treat in this course, we're generally going to encounter these two cases, and the special case of d2u dx squared equals 0 is not going to concern us. Now let's look a little bit more carefully about what happens around an equilibrium point. Let me scroll down here and I'll use a plot that only has a single equilibrium, a single stable equilibrium in any case. And since we're dealing now with the conservative forces, that means the total mechanical energy is conserved. So that u plus t is a constant, and I can just say that that is here, right? So we have conservative forces, or just a conservative force, means that we can say that E equals T plus U equals a constant. And therefore, during the motion of the particle in this potential, the total energy is always the same. It's always equal to E. So if we are at some particular position here, some x, that means that we can say that, okay, this now, that's going to be U, and the difference here up to E, that's going to be the kinetic energy T. When you are at the equilibrium point, then your kinetic energy is maximum and your potential energy is minimum. And once you reach these points here, then all your energy will be potential energy. And you cannot move any further to the right here, or any farther to the right, or any farther to the left than these points, because that would require the total energy to be less than just the potential energy. And that's not possible because there's no such thing as negative kinetic energy. Kinetic energy is 1/2 mv squared and always positive. So these points here, we call them A and C. These are turning points. So the motion of a particle in this potential is going to look either it will be at rest at the bottom of the well, or it will move back and forth between the turning points, but never outside. So to state this mathematically, so if x equals, let's say, A, that means that the total energy is U of C, which means that the kinetic energy is 0, and therefore the speed in this case is also 0. So no further motion to the left. And that's why C is a turning point. Now, what is often done is that you pick a convention to set, we've already seen this actually, that the potential at infinity equals 0. If that's the case, you can just look at the total energy to see what the behavior of your particle might be. If that's a convention, we have that energies greater than 0 are what we call unbound. And if the energy is less than 0, then the particles are bound. Perhaps becomes a little clearer if we look at this graph here. If the total energy is less than 0, then there's a maximum distance that the particle can travel. Let's say, for instance, that the energy is here. then we know that the particle is confined between these 2 points here and here. So it's bound to a finite interval. However, if the energy E prime here is greater than 0, then the particle can move all the way to infinity. It can move over an infinite range. There are still ranges that are excluded, perhaps, but there's no finite interval within which your particle is confined. Actually, I should make that greater than or equal to 0. So far, everything we've said are things you should have seen in freshman physics, which is why I'm going through this relatively rapidly. But the next step you may not have seen before. What we're going to do now is find a formal solution to the motion of a particle in a one-dimensional potential in general. And this is something we can do because we're working in one dimension. That makes life simple. So again, we're working with conservative forces. So the kinetic energy plus the potential energy equals the total energy. And we can also write that, therefore, that the kinetic energy is the total energy minus the potential energy, which does depend on position. Kinetic energy is 1/2 mv squared, or if we like, 1/2 mx dot squared. So now in principle we have now a differential equation that we can try to solve. Okay, so if we invert this, we multiply by 2, divide by m, and take the square root, we get that x dot equals the square root of 2 over m times the square root of e minus u of x, like that. And then we know that, of course, this is equal to the x dt. So we multiply by dt and divide by anything that contains x. So we get all the time variables on one side and all the position variables on the other. And we then end up with like that. Okay. Now, what we do is what we normally do. We just integrate. So this goes from 0 to t prime. This goes from your initial position, which would be x0, and your present position, x. We change the variables inside the integrals to primes as usual. And this gives us now the formal solution, that the time, that's what this integral becomes, just equal to t, is now equal to square root of m over 2 times this integral. So we have the x prime divided by the square root of e minus u of x prime. All right. So that's the formal solution. Now, nothing says that you are in general able to solve this. In most cases, in fact, this is going to be a relatively difficult integral because you're 1 divided by the root of a constant minus your function. For most functions, that doesn't have a closed form solution. But we will use one particular case when we actually have a closed form solution, and that turns out to be a very important one. So let's take the example of the potential equal to 1/2 kx squared. That's a parabolic potential, something like this, although I've added a constant here just to make it a little clearer what it looks like. We can pick this level here, for instance, as perhaps your energy. Then we get turning points, and they will, in this case, because the minimum here is located at x equals 0, we look at it at, let's say, A and minus A. And because of this form, we can immediately now say that the total energy equals 1/2 K A squared. Hopefully you can see that. This is because when x equals A, the energy is only potential. So at x equals A, the energy is just 1/2 Ka squared. And that's the total energy. Conservative forces again, so that doesn't change over time. All right, so with that, we can now actually try and solve this, this integral. So specifically what we have, and we're going to start at point A over here. And what I've done now, I've used the fact that E is 1/2 Ka squared. So I can basically replace this with 1/2 Ka squared, and that makes it possible for me to take 1/2 of K out of the root. We should make sure that we're actually going to use primes here everywhere, just to distinguish from the limit. Okay, then we'll make a change to variables. That is xi, by the way. It's not an x, it's a Greek letter xi. All right. Now, as it turns out, the primitive function, or the antiderivative of 1/2 squared of 1 minus x squared, or the xi squared, is equal to either arc sine of x or minus arc cosine of x. It's actually the same function. So we're going to pick the second one, and we will then get turns out that the arc cosine of 1 is 0. That's because cosine of 0 is 1. This is equal to 0. In principle, plus n times pi, but we're going to just pick n equals 0. That's perfectly fine. So now we get that the time here equals minus the square root of m over k times arc cosine of x over a. We can then invert that, so we get that x over a equals cosine of t times the square root of k over m with a minus sign in front. Now cosine is an even function, so cosine of minus something is cosine of plus the same value. So this gives us our final result here. Which you should recognize as simple harmonic motion. And I'm going to bring in the potential there again, so you can see this is for this particular case here of potential equals 1/2 kx squared. So we have oscillatory motion between the turning points. So as time goes by, x changes from plus a to minus a and then back again. And the frequency with which this happens is the square root of k over m, which, if this were, for instance, the potential of a spring, you would recognize as the correct answer, right? If you have say a weight here that's attached to a spring, it's moving on a wall, then the motion of this obeys this formula. You were told this in Physics 2305. And now we've actually derived it through a slightly backhanded way, but we got the right result in any case. Now, simple harmonic motion is a very important subject, and we're going to deal with that extensively. It's the subject of chapter 5 of the book. Okay. So we will deal with that in several upcoming videos, but for our purposes right now, we'll stop right here, and in the next video we're going to continue to work with motion in one dimension, but generalize it to motion along a curved path.